Hey guys, it's Mr. Lyle. This is Honors Chemistry. This is our first video, one of many, I suppose. Um, I would suggest anytime we have a video, get out a pen and some paper and take notes. Often afterwards, there's going to be a very short quiz that will count as a daily grade. So it's good to have notes. Last term, we finished the term by talking about gases and their properties and looked at several different equations that we could use to make predictions about gases. When we start this term, we're starting with two other phases, the liquids and solids. What you'll notice about liquids and solids is that they're pretty similar to one another, but quite different from gases. And so the goal of this video today is to look at those differences that we see between gases and liquids and solids, and also to just kind of refresh our memories about some of the things that we already know, but will end up being pretty important as we move forward. So the the focus of today's video is going to be on a simple molecule called fluorine. Fluorine is F2. It's one of our diatomic molecules. And just as a refresher, if you have a periodic table and you look at the atomic mass of fluorine, it's right at 19 grams per mole. And if I wanted to calculate the molar mass of this molecule, I would say that it's 2 times 19 because it's F2. So the molar mass of this molecule is 38 grams per mole. Additionally, one thing that's going to be helpful as we move forward is that we're able to count the total number of electrons in the molecule, not just the valence electrons, but all of them. So we're used to looking at valence electrons where we look at the outermost shell, and for fluorine, it would be 7 per atom or 14 total. But the total number of electrons in a fluorine molecule includes the inner shell electrons. Probably the easiest way to calculate it is to look at the atomic number of fluorine, which is 9. And while the atomic number describes the number of protons in a neutral atom, it also tells us about the number of electrons. So again, if I recognize that there are 2 atoms of fluorine, each with 9 electrons, then the total number of electrons would be equal to 18. Okay. And the last thing that I want to refresh our memory on is that fluorine itself is a nonpolar molecule. And just a reminder of what that means. To say something is nonpolar means that there's an even distribution of the electrons. So those 18 electrons that we find in fluorine are pretty evenly spread out. It's a neutral molecule. There's not one side that's negative or positive. It's neutral throughout. And how I know that is that it's a very symmetrical molecule. When we see something that's symmetrical, it tends to be nonpolar. Okay. When we get to future videos, your ability to calculate molar mass and total number of electrons and decide if something is polar or nonpolar is going to be really important. But back to today's story, we want to know why fluorine as a gas, or how does fluorine as a gas differ from fluorine in the liquid phase? And I think you can really see it in the 2 pictures presented below. On the left-hand side, I've presented fluorine as a gas. I've presented 5 molecules of fluorine in the gas phase. And on the right-hand side, I have fluorine in the liquid phase. And I still have 5 molecules. But there's a major difference. On the left-hand side, as a gas, we recall that the molecules spend most of their time by themselves. Yes, they collide with one another, but most of the time they're not near one another. And the easiest way to achieve that, if you remember, is to make sure that those molecules are moving at a pretty fast rate. And that's achieved when the temperature is high. So we expect molecules to exist in the gas phase at high temperatures. And specifically, when we talk about gases, we also often refer to their pressure or volume. When molecules have very little pressure or have a large amount of space to roam around in, they tend to exist in the gas phase. And so for gases, we would expect that there's going to be a large volume of available space. And because of that, the pressure is going to be essentially low. That's Boyle's law, an inverse relationship. In the liquid phase, we talk a lot less about pressure and volume, but temperature still matters quite a bit. If I look at the liquid particles, they're close together. They seem to be stuck together. Now, in the liquid phase, they can still move quite a bit. They can move past one another, but there's something that keeps them attracted to one another. And we want to kind of set the stage by saying, what are the conditions that are going to help us to achieve that ability for them to stick together? Well, the first thing that you want to do is slow them down. And so we would say that in the liquid phase, molecules tend to exist at a much lower temperature. That's because their speed is pretty slow. And you might be able to get them to get closer together if we make sure that the pressure's relatively high. But again, we don't really talk too much about pressure or volume when we talk about a liquid. I think the big difference, kind of the take-home message of this video, is that there's a lot of separation between the particles in the gas phase, but in the liquid phase, they're closer together. And we've set up some conditions that will kind of facilitate making that happen. We want gases to exist at a high temperature. We want liquids to exist at a low temperature. But the question that we have moving forward, the big question possibly for our next video, is what makes them stick? There's nothing about moving slow necessarily that says molecules are going to stick together when they're moving slow. So why did they stick together? And that's when we'll introduce the idea of intermolecular forces and London dispersion forces. But that's for a different video. Okay, thanks, and I'll see you soon.